XRD characterization of nanomaterials. The objective of this characterization technique XRD is to find out the crystalline structure, the size of structure and the shape, defect structure, thickness of the thin film. XRD mechanism. How does the XRD techniques works? Actually, this technique is based upon the diffraction of X-rays. In a vacuum tube, we are producing the X-rays like from the two opposite electrodes, negative and the positive electrodes. When there is a high potential difference between the two electrodes, the electrons are emitted from the negative plate to positive plate. That electrons falls on the tungsten plate, which produce the X-rays from that plate. And that X-ray beam, if you throw that X-ray beam on our sample, suppose to the sample nanomaterials we are going to characterize, then we need to throw the X-ray on the crystalline sample. As we throw the beam on that sample, let us assume the sample is copper, and as the X-ray is falling on the surface of copper, that get diffracted at the different angles, like 10 degree, 30 degree, 35, 40, 43.2 degree, 50. So at the different angles, we receive the different intensity of X-rays, and that diffraction angle is actually directly tells about the wavelength of diffracted X-ray. There is the relation between X-ray wavelength and diffraction angle and the intensity of diffracted X-ray from the nanomaterial sample like the copper. This angle here, the beam is coming, is going out, it's reflected from here, scattered from the surface. This angle is equal to that angle. Both angles are similar, and this is the length, the difference between two layers of the crystals, the atomic gapping from this layer to this layer. This is the gap between two atomic layers. This gap is called D. We called it the D. So it's this angle is equal to that angle. Then this becomes a triangle, and that distance becomes the d sine theta. As this distance is analogous to the wavelength, this. So d sine theta and the d sine theta here. There are two d sine thetas, which is equal to lambda. So this d sine theta is lambda half. Then the lambda half becomes d sine theta, and that forms the Bragg's law. The equation becomes like lambda is 2d sine theta. This is called Bragg's law. Here the n, if the reflection is from the first layer, then n is 1. For the second layer, n is 2, 3, 4, so on. That depends on the layer of reflection. So here, this is the first layer, so n is 1. So that becomes the n lambda equals to 2d sine theta. So lambda equals to 2d sine theta. This is your Bragg's law. And this law we are going to use in XRD characterization of nanomaterials. If the conditions are given already during the experiment. While we are doing the experiment, we are given the wavelength of diffracted X-ray, we are taking here lambda is 0.154 nanometer, which is equal to 1.54 angstrom, and copper radius, the atomic radius of copper is 0.128 nanometer, where the diffraction angle we can measure during the XRD experiment is, suppose we are getting the highest intensity at the angle 43.2, so then our 2d 2 theta is 43.2 degree, and then our theta is 43.2 divided by 2. When we put these data into the Bragg's equation, then we can actually measure the d, the distance between two atomic layers of copper as our sample. So d becomes like that. We are putting the wavelength here, you know that. I know the theta. Then d is equals to 0.209 nanometer. And furthermore, to find the Miller indices, we know that d is equal to a upon root L square plus h square plus k square. So d equals to that, and we already find out from the Bragg's law the d is 0.209, sorry, 0.209 nanometer. When we put this value into that equation, then we can easily find out the Miller indices of the crystal structure. So let us put these values in the equation. As copper radius is 0.128 nanometer, and copper is a face-centered cubic structure, then the radius and the crystalline parameter relations is r equals to a upon 2 root 2. So here r is 0.128 nanometer. Then we can find out the a. So let us put these values in the equation. Here d is a upon root L square plus h square plus k square. So it turns out to be d equals to that value, which is equal to, from the Bragg's law, lambda upon 2d sine theta. We know the d is from here 0.209 nanometer. When we put these values into that equation, as we plug in these values in that equation, we find out the d value is this, that d. This is the d value, and we put the d value in this equation. We find that root L square plus h square plus k square is equals to 1.732. As we get this value is actually belonging to the Miller indices, these L, H and K. So there is root. We are squaring both the sides. We get that square of this 1.732 is 3.0. So this equation is actually the x square plus y square plus z square equals to 3. So which condition satisfies that? And as we know that the FCC structure, the parameters of crystal structures are 111, 200, 220. So when we put these values into this equation, and the value which satisfies that equation is actually the satisfying Miller indices. So if you put in this equation LHK, L is 2, H is 0, K 0, we get that L is 2, H is 0, K is 0. We get 4 equals to 3, which is not true. Then we put 2 to 0 in that equation. L is 2, H is 2, K is 2. We get 8. 8 equals to 3, which is not true. So once again we are trying this one. 1 1 1. When we plug these value in that equation, we get L is 1, H is 1, K is 1. And we plug these equation into these values in that equation, we get actually 3 here in the left side, and we already know that the right side is 3, so 3 equals to 3, which is the possible value of Miller indices. So finally, by the experimental data and during the Bragg's law, using the Bragg's law, we find out the Miller indices. Actually this is the most suitable Miller indices, 1 1 1 for the copper. So this is for copper. So finally we get that the Miller indices are 1 1 1 possible. So the observed data are analyzed by the intensity and 2 theta graph. And intensity and 2 theta graph we are actually achieving from the diffraction of X-rays on that copper crystalline. So the graph is analyzed, and that graph tells the many information about the atomic packings, atomic arrangement, and their crystal structure, their defect, and the shape of the peak. So in the next, there is a 2 theta and intensity graph. We will just analyze. And the data we received from the XRD diffraction pattern is just here. This is a graph of angle and the intensity of diffracted X-ray on the crystallite sample. These fluctuations are actually just like the fingerprint of the sample. These fluctuations, these peaks, tell everything about the composition of crystalline, its atomic packing, the arrangement of atoms, and the size of particles, and the disorder defects, crystal structures, phase, and many things. So each we can see that the 2 theta 20 30 50 60 70 80 at the angle of 30 receives that peak. This peak is mostly the maximum height rather than this and this. So we see this, the height of this peak is up to that. At the intensity 7000, a peak is observed at the angle of 30. 2 theta equals to 30, then theta equals to 15 degrees. So the height of peak is the peak height, which is actually the intensity of the X-ray, which is diffracted from the crystallite. Point A, that was the point A, peak height. Point B is the half maximum point. This, the total height, the half of that height. At this point, if you take the width of that peak, then we call it the peak width, which is abbreviated by beta. And this point is called half max point, or we can say the mid max point. Okay, this like the third one is C, the area of this peak, area under that curve. The area under that curve actually tells about the crystal structure and phase. And fourth is D, peak shape, abbreviated by DV, peak shape. And the fifth one, peak position. Peak position, we achieve the maximum peak at angle 30. 2 theta is 30 and intensity is 7000. This one, that here. So this peak profile, that peak profile is actually the graph of angle and the intensity of X-ray refracted from the crystallite. The copper, we used copper here. The copper radius 0.128 nanometer and the wavelength we used 0.154 nanometer. So these data we actually received from the X-ray diffraction during the experiment. That graph actually tells the many things about the crystallite. Here the copper, we can find out the many things about the copper, like peak height. The peak height is actually telling about the maximum intensity we are receiving at the angle of 2 theta is 30. Peak height, maximum intensity we receive, and peak width, this one, peak width. This tells about the crystallite size, strain, disorder, defects. Peak area, under that area, the peak area is telling about the crystal structure and the phase of the crystallite. Peak shape, this shape, the shape of this peak is telling about the crystalline size and defects, and the position of the peak, this at the 30 and maximum height is 7000. This position is telling about the d spacing, the spacing of the atoms, atomic packing, the arrangement of atoms inside the copper crystallite. Lattice parameters, like we used in the last segment, that r equals to a.2 root 2. So lattice parameters a here also is determined by this graph. Lattice parameters is copper is a face-centered cubic crystal structure. So we received that the Miller indices L1, H1, K1, 1, 1, 1. So these indices we received in the from the Bragg equation. So actually this graph is mostly useful, we received from the experimental data, and these peaks are telling about the many things about the crystal size and structures and lattice parameters and intensity of the peak and size, atomic arrangement inside the crystallite. So actually there is one more equation, scalar equation, which also we can use. We could find the many things using the scalar equation, like the average size of the crystalline. So the scalar equations we can use is k lambda t beta cos theta, which I told you already. The beta is peak width and dv is average particle size, which is actually the peak shape, which tells about the crystal size, particle size. Theta, the angle of diffractions we receive, is the maximum height at the 30. K is the scalar constant, and lambda we are using in this copper characterizations just 0.154 nanometer. So from that equation we can find out the scalar constant of the copper by that equation. So finally I see that the XRD is a good method for homogeneous and single phase crystals in bulk to get the characters and to find out the characterization data using the XRD. And for if the sample your crystallite is heterogeneous and it has the multiple phases, then I don't recommend you the XRD is a good method for this. So XRD is good for the single and homogeneous crystallites, and also good to find the characterization data for the nano and thin films. For the multiple phases, we actually using the scanning electron microscopy and atomic force spectroscopy, and so on many methods. So thank you.